thanks so much for the introduction.
There's no rabbit in it, we're going to riot.
This is, I think, the only rabbit, so should be safe. So my work is in a field known as symplectic and contact geometry and topology. So I'll mostly focus on the contact side of things. And where does symplectic and contact geometry come from? Well, it comes from generalizing the formalism of classical mechanics. And so phase space turns into a symplectic manifold, essentially because the symplectic form, which is a closed non-degenerate 2 form, you can think of that as intertwining the position and momentum. And then back in the day, Euler and Lagrange figured out that the equations of motion minimize action, and action is given in terms of the difference between the kinetic and potential energy. And then about 50 years later, Hamilton and Jacobi figured out how to turn these n second-order differential equations into a system of first-order equations where you have 2 n equations. And so solving first-order equations can be a bit more amenable than trying to solve like second-order differential equations. So this Hamilton-Jacobi framework is really nice. And then also in the Hamilton-Jacobi framework, your motion is governed by conservation of energy, and that's a very natural thing to think about in a physical system. And when you become a mathematician, you stop caring about whether or not the quantities or functions you're thinking about relate physically to anything. And so we now just call like any smooth function a Hamiltonian, even though like originally the Hamiltonian should have like been some kind of energy function. So it would have been like the sum of the kinetic plus the potential energy. And then what happens is you can write down the flow lines of a Hamiltonian vector field, which is given by a 90-degree rotated gradient of the Hamiltonian if you're working in standard coordinates. And then the flow lines of that vector field are going to be solutions to the equations of motion. And phase space turns out to be secretly a symplectic manifold. And then the way that contact geometry kind of first entered the picture is if you were to look at a regular energy level set, that's going to be a codimension 1 manifold, and it's going to play nicely with the symplectic structure. And you'll be able to get a contact form, which realizes the symplectic form. And then if you restrict the Hamiltonian vector field to the level sets, then you're going to have what's called a Reeb vector field. And so the analog of the Hamiltonian vector field in the contact setting is called the Reeb vector field. And then contact geometry actually shows up in a lot more situations than symplectic geometry does. So if people have seen like symplectic talks before, they may or may not remember that the only even dimensional sphere which admits a symplectic form is the 2 sphere. That's not the case in the contact realm. Like it's much easier to have a contact structure. And indeed, we know for every odd dimensional contact manifold, it admits a contact structure. And so a lot of geometric problems can be recast in terms of a contact geometric setting. So you can reinterpret geodesic flow in terms of the Reeb flow on a unit cotangent bundle. And then there were models in optics and thermodynamics. You also see it show up in surface dynamics, and then 3-body problems where you're looking at a satellite, a moon, and a planet. Okay, so that's like the physical motivations. Now we move more into like the modern formulation of contact geometry. So a contact structure is going to be a maximally non-integrable hyperplane distribution. If it's been a long time since you thought about like the Frobenius theorem and involutive and integrable distributions, you can kind of pretend that maximally non-integrable means nowhere integrable, but actually it's a stronger condition to be maximally non-integrable. But if you think about nowhere integrable, that means that nowhere can you ever locally find a codimension 1 submanifold whose tangent planes agree with the distribution. So here, the hot pink thing is supposed to be an example of an integrable distribution where the distribution is realized by the tangent planes of the surfaces which foliate your manifold. And then on the left-hand side, the purple are 4 different slices of the standard contact structure for different z values. And if you like squint really hard at that, you could probably convince yourself that there's no 2-dimensional surface whose tangent planes agree with this given collection of planes. And there's a slightly more friendly way to figure out when the kernel of a 1 form determines a contact structure, which is just to do lambda wedge d lambda to the n and see if you get a volume form. And if we computed d of dz minus y dx, we'll get a dx wedge dy. And if we do lambda wedge d lambda, we're going to end up with a dx wedge dy wedge dz, which we all hopefully agree is a pretty reasonable volume form for R3. And that's the same thing as saying that d lambda restricted to its kernel is non-degenerate. And this condition that d lambda restricted to its kernel be non-degenerate is also equivalent to saying that its kernel equipped with d lambda is a symplectic vector space. And then in symplectic geometry and in contact geometry, we have something called Darboux theorem, and that just says that locally you can always transform a point in a contact manifold into, you can shift it to be the origin, and the contact form takes on the standard contact form structure in R2n plus 1. And so this tells us that locally, in some sense, all contact structures look the same. And so that means that there's no local invariants like curvature for us to study. And the subject turns into one that's kind of like a strange mix of both geometry and topology. And so kind of the game that we'll start to play is we want to build chain complexes, which are generated by closed periodic orbits. And then the differential is supposed to count some pseudo-holomorphic curves, and that the computation of the homology doesn't actually depend on the choice of contact form or on the choice of J. And so you see kind of like a pretty different flavor of methods and theorems than you would in like a more differential geometric subject. So the analog of the Hamiltonian vector field is going to be the Reeb vector field, and it's uniquely determined by these two equations. So the first one is that you want lambda of R to be 1, so you can think of that as a normalization condition. And the second condition is that you want the contraction of R with d lambda to be 0. So that's giving you a splitting of the tangent bundle of every point in your manifold into the contact distribution and the Reeb direction. And this also tells you that the flow of the Reeb vector field will preserve the contact form and also the contact structure. So you want to think of the Reeb vector field as being transverse to your contact planes. So I have our example on R3, we have lambda is dz minus y dx. So if we want the contraction of a vector field with lambda to be vanishing, a good option, because d lambda is going to be a dx wedge dy, is to make it be something involving a ddz, and then you can check that the normalization condition is verified if you just pick dz. And so then the flow of the Reeb vector field is just moving upwards along the z-axis in time. And so while the Reeb vector field isn't perpendicular to every contact plane, it is always transverse to every contact plane. And then I have like a bunch of words that will show up throughout the talk. So we now have like a slide or two of words. So the Reeb flow is defined in the usual way, where you just want the time derivative of the flow to be the same thing as R applied to the flow. And then in the study of contact topology and contact geometry, we're going to be especially interested in closed periodic orbits. And so we're also going to only care about the orbits up to reparametrization. So we just care about their image inside of the manifold. So they're going to be maps from R mod TZ into the manifold Y. T you can think of as the period of the Reeb orbit. We're going to make T be positive. And in the symplectic realm or contact realm, T is often said to be the action of the Reeb orbit. So you would get it by just integrating lambda along gamma, and you would get your big T. And then we want gamma dot to be equal to R of gamma. And we'll say that a Reeb orbit is embedded whenever this map is injective. And so it turns out when we build some of these homology theories, sometimes we want to just care about the embedded orbits. Sometimes we want to care about their iterates, but we want to be able to distinguish an embedded orbit from a multiply covered one. And then there's going to be certain behaviors that the Reeb orbits exhibit depending on the eigenvalues of their linearized return map. So if you have an embedded Reeb orbit, after you make a choice of unitary trivialization, you can take the derivative of the flow restricted to the hyperplane distribution along the orbit, and you'll get a linearized return map, because when you start at t equals 0 and end at big time t, you're going to be back to the same point, but you're looking at some path of symplectic matrices, and the starting matrix might not be the same as the ending matrix. And so you're going to look at the eigenvalues of that big time t matrix. And then if one is not an eigenvalue of the linearized return map, we say that gamma is non-degenerate. And you want to kind of think of this as like a Morse condition. So if all of the Reeb orbits associated to a contact form are non-degenerate, it means they're going to be isolated. And then in dimension 3, if we want to look at non-degenerate orbits, that means that in order to get a product of eigenvalues to be 1, we're going to either need them to be complex conjugates which live on S1, in which case we would say that the Reeb orbit is elliptic, or if you have pairs of real eigenvalues E and 1 over E, then you would say that your Reeb orbit is hyperbolic. And then I didn't really have like a good spot to like talk about J, so I just put J on this slide. But I mentioned that we have a splitting of the tangent bundle of Y into this contact plane and into the Reeb direction. And so if you R cross Y, you'll get an even dimensional thing. And if you intertwine the Reeb direction with the R direction in a way like complex multiplication, then you can construct an almost complex structure on R cross Y just by extending any complex structure on the symplectic vector space to 1 on all of R cross Y by intertwining the Reeb direction with the R direction. And then we have like a certain number of things that we want. So we want the J to be R invariant. And we want J to rotate the contact planes positively with respect to d lambda so that we get a Riemannian metric if we put in J to d lambda. And we'll see J show up in a couple slides. So as an example of something a little bit more exciting than R2n+1, we've got the 3-sphere, and all odd dimensional spheres are going to be contact manifolds. There's 2 different ways that you could think about the odd dimensional sphere, and it turns out that they're equivalent from the perspective of contact geometry. So either you can think of the odd dimensional sphere as just a hypersurface inside of Cn, or you can think about it as a S1 bundle over Cpn. And if you're thinking about it in terms of the S1 bundle over Cpn, then the derivative of that S1 action actually realizes the Reeb vector field. And so the Hopf vibration is essentially the Reeb vector field. You can go through a computation in coordinates if it's reassuring. And Patrick Massot has this nice illustration where the hot pink ray of twisting planes is the contact distribution, and then the purple lines are the flow of the Reeb vector field, and they're preserving the contact distribution. And then Niles Johnson has like a really nice animation of the Hopf vibration. So we're looking at S3 mod S1, that gives us an S2, and then every point in S2 lifts to a circle upstairs inside of S3, and the color of the point downstairs corresponds to the color of the fiber. I have this animation, so there's like some cool, well, we'll just like watch the whole animation. So there's some cool things to like notice. So if you trace out any closed loop downstairs on S2, that will lift to a torus upstairs. And this video also shows you how you can realize the 3-sphere by gluing 2 solid tori along their common boundaries. So you have 1 solid tori over the northern hemisphere, 1 over the southern hemisphere, and their common boundary is the torus over the equator. Every orbit is going to link with every other orbit exactly once. Later on we'll talk about J-holomorphic curves, and there may be kind of like a question of like, how do we relate these counts of J-holomorphic curves to something that we might see in Morse theory? And so the idea is going to be that for a suitable choice of a Morse function on the base, where you would realize like a gradient trajectory, there will be holomorphic curves upstairs, which are actually in 1-to-1 correspondence with the gradient trajectories on the base. So if you like look really carefully at what's going on over a gradient trajectory on the base, and you thought about like crossing the picture of S3 with R, then you could kind of visualize what pseudo-holomorphic curves look like. And then when we get to like talking about some Floer theories, I'll use kind of like this S1 bundle perspective as like a, well, I don't want to call it like a toy example because it's not really that much of a toy. But more generally, you could consider like an S1 bundle over a sphere or over a Riemann surface, and then you can take a negative Euler class. So the Hopf vibration is just negative Euler class 1. But if you wanted to realize a lens space, you would take negative Euler class P, and that would give you L absolute value of P1. So this kind of like construction is pretty nice and like lends itself to computations because you can typically relate the J-holomorphic curves to Morse flow lines.
It's a bit trippy.
Yes, it's really nice, I think. And this is like the best kind of like approximation to a Reeb vector field, which is not trivial. So
Is this video publicly available?
yeah, it's publicly available. So if you like Google Hub vibration, this should be the first link. I downloaded it from YouTube so I could embed it in my slides. And Niles Johnson has like a whole page and like talks about all the different fun things to look for in the video. It's like a good thing to show to undergrads or even grad students. Okay, so now kind of the question is like, why do we care, or why is symplectic or contact geometry interesting? And so maybe one of the things that started to move the needle in terms of considering contact manifolds in their own right is something called the Weinstein conjecture. And so this is the modern formulation of it. This isn't how it appeared in 1978. But now today we would say if you have a closed, oriented, odd dimensional manifold that admits a contact form, then the associated Reeb vector field has a closed orbit. And the fact that this conjecture has stood the test of time is interesting if we go back and think about the Seifert conjecture from the earlier 1900s, which was disproven. So that said that any vector field on a sphere admits a closed periodic orbit. And that's been shown to be wrong under all kinds of assumptions about the vector field. But it turns out that if you're a Reeb vector field, you will actually have to admit a closed periodic orbit if you're a three sphere. And the kind of history of the Weinstein conjecture was that, well, it's kind of confusing because I think Weinstein and Rabinowitz were working on these ideas at the same time, but they had papers that got published in slightly different years. So Weinstein proved this for convex hypersurfaces inside of R2n, where he considered the restriction of the Hamiltonian vector field to the contact hypersurface or the convex hypersurface. And he showed that that restriction to this regular energy level had to admit a closed periodic orbit. So that was kind of the first inkling that there was something interesting going on. And then Rabinowitz proved it for star-shaped hypersurfaces inside of R2n. And so you're going to be star-shaped with respect to a point if you take a ray going out of every point and you intersect your hypersurface exactly once and transversely. And Weinstein was the referee to Rabinowitz's paper.
Actually, second. So this was simultaneously, and then Rabinowitz wrote another one. And Weinstein was the referee of the next one of Rabinowitz.
Okay, so Rabinowitz has two star-shaped ones?
No, star-shaped and the slightly more general one.
Okay.
And, Weinstein was the referee of the next one.
The next one, okay. Weinstein was a referee of one of Rabinowitz's papers.
Yeah.
And then in that same journal, there was like a short notice announcing Weinstein's conjecture because you realize that this star-shaped condition is actually a contact type condition. Oh, and a fun fact that's not in Helmut's Floer book that Alan told me is that when Alan initially submitted his convex hypersurfaces article to the Annals, the editor said like, this is lame, nobody cares. But Alan had correspondence from Moser and Rabinowitz saying that it was like the best thing since sliced bread. And so he sent the mimeographed correspondence to the editors of the Annals, and they retracted their initial opinion and decided to let him publish it. So if you have like some old correspondence with Moser telling you that like your theorem is like great, then maybe you should keep that. Okay, and then in the 80s, Viterbo, Hofer, Floer, and Zender proved the Weinstein conjecture in a variety of circumstances. And I think one of my favorite stories, which is not so mathematical, was that Viterbo had a CNRS postdoc, and he got out of doing military service by doing volunteer work in a third world country. And that volunteer work was teaching calculus at Courant in the 80s. And Helmut was an assistant professor at Rutgers at the time. And apparently the two of them loved to meet in Penn Station and eat McDonald's hamburgers. So they proved while eating McDonald's hamburgers a variety of results about the existence of closed periodic orbits of various Reeb vector fields. But in all these kind of like iterations, you were always in some kind of setting where you were looking at a contact type hypersurface inside symplectic manifolds. They started with like the cotangent bundle, and then they upgraded to like symplectic manifolds, and then it was proven in like different special cases. And then kind of the big breakthrough happened in the 90s and in the 2000s. So I don't know, Helmut, where this ranks in like your top theorems. I don't know if you have like an ordered list. But okay, yeah, so probably a pretty good theorem. So you proved it, Helmut proved it for S3. He used holomorphic curves inside of a symplectization. And he was the first person to realize that you could transport pseudo-holomorphic curves, which were primarily restricted to having targets be closed symplectic manifolds, to contact manifolds by doing R across the contact manifold. But there, the compactness phenomenon are maybe, let's say, a little bit more exciting. And you, in fact, have some kind of a failure of compactness, which allows you to establish the existence of a periodic orbit, because you have a plane break off that has to limit on a periodic orbit. And Shira alluded to some of this in her members colloquium a couple weeks ago. And then Taubes used something called Seiberg-Witten-Floer homology to prove the Weinstein conjecture for any closed-oriented 3 manifold that admits a contact form. And there, what he was doing was showing that a sequence of spinors would actually have to converge to a closed periodic Reeb orbit. And then the tools that were used after 1985 involve kind of some mix of pseudo-holomorphic curves and Floer theories. And then this is kind of, this is, I think, my favorite quote from Helmut. So I have to like remember the diction advice that Miles has given me. So yeah, okay, why did I come into symplectic and contact geometry? So it turned out I had the flu, and the only thing to read was Rabinowitz's paper, where he proves the existence of periodic orbits and star-shaped energy surfaces. It turned out to contain a fundamental new idea, which was to study a different action functional for loops in the phase space rather than for Lagrangians in the configuration space. And this goes back to this whole like Euler-Lagrange formalism versus the like Hamiltonian formalism. And Moser had said, he actually written in a paper that this action functional for loops in the phase space was not suitable for an existence proof. So Rabinowitz really did have like a fundamental new idea in this paper. And then Helmut went on to say, which actually, if we look back, led to the variational approach in symplectic and contact topology, which is reincarnated in infinite dimensions in Floer theory and has appeared in every subsequent approach. He concluded by saying that, yeah, the flu was very good. So this kind of, I guess, motivates the shift to the more like modern study of contact and symplectic structures. And so I want to start by just saying a few words about Floer theory and Morse theory. But I guess here's like a good place to pause and see if there's any questions. Okay, so what is Morse theory? So we're going to look at non-degenerate smooth functions on a manifold, and we want to have some kind of reasonable Riemannian metric. So the non-degeneracy condition just means that we want the Hessian to be non-vanishing, so we can look at its eigenvalues, and then the G being a reasonable metric means that we want the unstable and stable manifolds of flow lines to intersect transversely. And then you say this pair is more smale. The chain complex is going to be generated by the critical points of the Morse function. The gradient is going to be given by the number of negative eigenvalues of the Hessian. And then the Morse differential is going to count index difference 1 trajectories modulo an R action. And those index difference 1 trajectories need to be trajectories of the negative gradient flow equation between critical points. And Floer kind of like souped up this version of Morse theory, thinking about it from the perspective that Witten had in the 80s. And he constructed something called what's now called Hamiltonian-Floer theory, where he had a symplectic manifold M equipped with the symplectic form omega, and then he considered certain time-dependent Hamiltonians, and then he had a J. And what happens is that the generators of the the generators of the Hamiltonian-Floer complex are the 1 periodic orbits of the Hamiltonian, and then there's this action functional that you can write down, so that if you look at its critical points, you precisely get the 1 periodic orbits of the Hamiltonian vector field. And if you're good at taking derivatives, you can compute sort of the gradient of that action functional, and you'll realize a J-holomorphic curve equation that's been perturbed by a Hamiltonian vector field term. And then by counting index difference 1 solutions to that perturbed Cauchy-Riemann equation is how Floer constructed a differential. The reason why Rabinowitz thought that you couldn't use this kind of action functional in any way is because Moser, sorry, not Rabinowitz, Moser. Is because the grading doesn't make sense from Morse theory. You're gonna end up with an infinite number of negative eigenvalues, and you're not even gonna be in a situation where the difference in the number of infinite eigenvalues gives you a finite number. So instead, you have to use something called the Conley-Zander index, which is a sort of winding number associated to arcs of symplectic matrices. And you get these arcs of symplectic matrices by linearizing the Hamiltonian flow. And those turn out to govern a Fredholm problem that's given in terms of the linearized D-bar equation. And so there's kind of some small miracles that occur that allow you to actually conclude that your moduli spaces are cut out transversely and are manifolds and can be compactified. But Floer had exactly the right number of technical conditions to kind of have this dream realized and be able to show that the theory he constructed was actually isomorphic to Morse homology. And then you know that Morse homology is isomorphic to singular homology. And so he used this theory and these isomorphisms to prove the Arnold conjecture. And then since the 80s, various people have removed certain technical conditions. They've also figured out how to change the fields, but I don't want to list like everybody's name on this slide. The idea behind the Arnold conjecture is just that the number of one periodic orbits of a non-degenerate one periodic Hamiltonian has to be bounded below in terms of the ranks of the homology groups of the manifold. So you're starting to see this like more topological interplay with symplectic manifolds, where you see global properties associated to vector fields defined in terms of a Hamiltonian, or in the context side, it'll be about a Reeb vector field, where those dynamics of the Hamiltonian or the Reeb vector field are really fundamentally governed by the underlying topology of the manifold itself. And then the analytic ingredients that you need are transversality. So you want to do some kind of implicit function theorem that's going to be Sard's-Mail, where you're looking at infinite dimensional Banach space bundles. And you want to say that this moduli space, which is given in terms of some zero section, is actually cut out transversely in a manifold or maybe an orbifold. And then you also need compactness, because you want to say that your zero manifold is compact, so your differential counts a finite number of things. Then if you want to say that d squared is 0, you need to be able to compactify your index difference to spaces of trajectories and show that that admits the boundary structure looks like a compact one manifold. And if you count the boundary points either with signs and when you're having a good day, or mod 2, you'll get 0. And then you have to do like a similar type of argument to set up the chain maps and prove the chain homotopy equation, so that you can actually conclude that the theory that you cooked up didn't depend on the various choices you made along the way. And then as kind of like a more down to earth recollection, I've just got like the Morse complex of the round sphere with the height function, and then the heart with the height function. In the case of the round sphere, you have a critical point of index 2. If you think about like water flow down the sphere, you'll have 2 different directions in which you can flow downwards, and those correspond to the 2 negative eigenvalues of the Hessian. And then if you sit down and think about what's going on with the differentials and you pass the homology, you'll get the same answer. And you start to see this kind of dichotomy between critical points of Morse functions and Reeb dynamics in these 2 theorems. So the first theorem is by Reeb. It wasn't stated this way, it was stated differently, but the content was the same. And so Milner in his Morse theory book explains how Reeb's theorem just falls out of a construction of Morse theory. So the idea is that if you have a Morse function and a compact connected manifold with only 2 critical points, then your manifold has to actually be homeomorphic to a sphere. And then in terms of like a contact interpretation is this theorem by Hutchings and Taubes, which generalizes some of the arguments that appeared in Taubes' proof of the Weinstein conjecture, which says that a closed contact 3 manifold always has to admit at least 2 embedded Reeb orbits. And if it admits exactly 2, then it has to be diffeomorphic to a 3 sphere or a lens space. And so we're still seeing these kind of like strong conditions about numbers of periodic orbits governing the underlying smooth structure of the manifold. Okay. So the rest of my talk, I wanted to say something about embedded contact homology. And then I'm giving a what is talk on Thursday where I will say more about embedded contact homology, though I realize that embedded contact homology is maybe like too advanced of a topic for the what is seminar, but I'll figure out something coherent to say on Thursday. So this is like the lightning fast recap of embedded contact homology. So it's a gauge theory for a closed contact 3 manifold that depends on the choice of a first homology class, and it's due to Hutchings. There's kind of 2 other gauge theories for 3 manifolds that are well known. One of them is Haggard-Floer, and the other one is Seiberg-Witten-Floer homology, and each one is kind of set up in a seemingly disparate way, but they tend to encode information that the other one might not see. And so they kind of each tend to have like a different range of applications, even though all 3 of these theories are isomorphic to each other. And as a chain complex, the embedded contact homology chain complex is going to be generated by Reeb currents as a Z2 vector space. And so Reeb currents is kind of like a funny description, except when you realize that the ECH differential is going to count J-holomorphic currents. And so the idea with a Reeb current is that you just want to care about the underlying embedded Reeb orbit plus some number which encodes a multiplicity. So a Reeb current of multiplicity 1 is just going to be an embedded orbit, and then you just care about convergence as a current. So you're just going to need to keep track of multiplicity and not an underlying geometric orbit, which is multiply covered. And then there's there's one condition about the generators, which is maybe not completely obvious why it's there, but it is necessary. And that's if you're a hyperbolic embedded orbit, you're only allowed to have multiplicity at most 1 if you're going to be included within the chain complex. And then the other like conditions are more straightforward. So you just want your alpha i's to be embedded Reeb orbits, and you want your multiplicities to be positive. And then you just want the multiplicity times the homology class if you sum over all I to realize whatever first homology class you picked in Y. And that will be the generator corresponding to that homology class. And then star is given by something called the ECH index. So it's a relative ZD gradient where D is the divisibility of the first Chern class of the contact distribution plus twice the Poincare dual of the class in H1. So that gives us something in H upper 2. The ECH index is kind of the most like magical thing about embedded contact homology. And it's very different from the Fredholm index, even though some of the components are familiar. So you're going to have a relative first Chern class, and you're going to have a Conley-Zander contribution, but the Conley-Zander contribution is going to be very different from the Conley-Zander contribution that you see when you look at the Fredholm index. And then the kind of like new ingredient that you see in the ECH index, which isn't present in the Fredholm index description of a J-holomorphic curve, is the relative self-intersection pairing. And it turns out that the ECH index just depends on the choice of a relative second homology class, which is also distinct from when you think about the Fredholm index, especially if you're just thinking about the index associated to a generator. And you can kind of think of the relative first Chern class as encoding something that's more contact topological. You can think of the Conley-Zander terms as encoding something that's contact geometric because it's seeing information about the Reeb dynamics. And then this relative self-intersection pairing sees something about algebraic topology. So the ECH index kind of nicely packages topological and geometric information in a very meaningful way. And then the ECH differential is going to count currents interpolating between index difference 1 orbit sets or Reeb currents. And it turns out that even though we're talking about currents in terms of geometric measure theory, you can actually realize the ECH differential in terms of disjoint unions of holomorphic curves. And it also turns out they're going to be somewhere injective. The kind of strange thing about the ECH differential is that you're not just going to be counting cylinders, or you're not just going to be counting genus 1 curves. You can have disjoint unions with kind of an arbitrary number of positive or negative ends. And then the individual curves can have arbitrary genus. You can prove that there is actually like an upper bound in terms of the genus. That's like more than we really want to go into. And then the important work from the early 2000s are the following two haikus, and maybe it's a little bit excessive to call them haikus, especially the second haiku, because it's 200 pages of mathematics with both Hutchings and Taubes' names on them. But it kind of encapsulates morally what's going on. So the first haiku is basically telling you that this ECH index 1 condition is actually like very special because it forces somewhere injectivity for the curves that you count. And that's really exciting because that means it gives you transversality. And that's not the case for Fredholm index difference 1 curve. So if you're working in symplectic field theory, if you're looking at Fredholm index 1 curves, they do not have to be somewhere injective. You can have like terrible transversality woes. But this ECH index 1 really like guarantees you something quite nice topologically and from an analytic perspective. And then the second haiku is just telling you that actually like you came up with a well-defined homology theory because it tells you that d squared is 0. But the way that you prove d squared is 0 is a bit more complicated because it turns out that you can have an ECH index 1 curve on top, an ECH index 1 curve on the bottom, but then you have to glue in a certain number of branch covers of trivial cylinders. And those are not cut out transversely, so you need something called obstruction bundle gluing. And you can do it. It's something that maybe I shouldn't say we know how to do from gauge theory, but that a subset of people know how to do in gauge theory. And that actually, because of the way the ECH differential is set up and the way that it was known to be computed in toric situations, it actually already encodes the fact that there's going to be these branch covers of trivial cylinders, which are not cut out transversely, but contribute to showing that d squared is 0. So there are a certain number of like analogies that break down with Morse theory, but in some kind of like magical way, the ECH like index and differential are well defined and make sense. Okay, so I should pause here and see if there's any questions or comments. Okay, go on. So then the next question is, why is ECH an invariant of anything? It seems to depend on the choice of contact form and on the choice of J, and you would expect to have kind of like similar transversality woes in cobordisms that you have in symplectic field theory. And fortunately, Taubes came to the rescue, and he realized that in his proof of the Weinstein conjecture, where he was showing that a sequence of spinors could converge to a closed periodic Reeb orbit, that there was actually a deeper mathematical thing going on in the background, which was that there was a canonical isomorphism between embedded contact homology and a flavor of Seiberg-Witten-Floer homology. And so he made that rigorous in a 500-page, 5-part paper that appeared in 2010. I think, well, this is like a side note. So Taubes writes all his papers in Word. So it's also very admirable that someone turned Taubes' 500-page Word document into a LaTeX document that was published in Geometry and Topology. It might also indicate why Taubes is so happy to publish everything in Geometry and Topology. Anyways, okay, so this theorem is also kind of, well, there are many things you could say about it, but one thing I wanted to note is that this theorem really tells you that ECH is stronger than being a contact invariant because the spin C structure that's associated to the contact structure really only depends on the homotopy class that the contact structure represents. And so morally, what's that saying is that if you were to compute ECH, even if you compute it for different contact forms which realize different contact structures, if those different contact structures give rise to the same spin C structure, you're not going to see a difference between your computations. And then also, if those different contact structures are in different free homotopy classes, there's a way to just shift that first homology class that you pick when you get ECH in order to realize the homology with respect to those different choices of lambda. And this seems like not desirable, but it turns out to be pretty important when you're actually trying to look at various applications of ECH. And so having this stronger topological invariance is actually a bonus that comes along. But usually nobody likes to talk about the isomorphism of Seiberg-Witten Floer homology, because that's like an even less appropriate topic for a what is seminar. And then what I want to say, the other kind of like nice thing about this isomorphism is that you don't run into these like, you don't need to use like virtual fundamental cycle techniques in order to establish invariants of embedded contact homology. And so that tells you that like when you are legitimately counting things with curves and relying on intersection positivity to define the ECH index, that's like all okay and not going to be destroyed when you like pass to some abstract virtual fundamental cycle to like extract invariants. The price that you pay though is that you have to like establish a canonical isomorphism at the level of the chain complexes between Seiberg-Witten Floer homology and embedded contact homology. Oh, and this like picture here, that's by Jason Hayes. So I didn't really want to say anything about Seiberg-Witten Floer homology, but you can think of them as kind of a Morse theory for the Chern-Simons action functional. And then you're looking at a spinner equipped with a U of 1 connection. And spinners are more special than sort of tensors or vectors because they can detect different homotopy class configure like changes in coordinates. And so there's something called like a belt trick where you can have like a twisted belt and then do some like complicated motion, which is not in the same initial homotopy class, but you can like untwist the belt, and a vector would not be able to detect that untwisting, but a spinner would. And then this like, there's actually a cool video by Jason Hayes where you have like a sphere with all these different like colored belts attached to it, and it goes through like a continuous transformation which becomes untwisted. And so the idea is that spinners can see those kinds of changes happening, and so that's part of what makes like Seiberg-Witten Floer homology so powerful and why people care so much about gauge theories when they're trying to understand 3- and 4-dimensional phenomena. So I have 15 minutes left. Okay, so what I wanted to do was do an example. The example that I want to do is to look at certain circle bundles over Riemann surfaces. So we're realizing a 3-manifold. And then we have some technical conditions about things, but the whole like idea is I just want to set up some S1 bundle over a surface so that the derivative of the S1 action is the Reeb vector field. And I want to do that in such a way so that I can just take I of a connection 1 form to realize a contact form on the bundle. And I also want this connection 1 form to be compatible with the curvature of the bundle, which is given in terms of the symplectic form. And if I set this all up correctly, then I call Y lambda a prequantization bundle over the surface sigma g omega. And then I have a variety of things apparent from this setup. So the first thing is that the Reeb orbits of R are going to be all the S1 fibers of this bundle. This contact form that's given in terms of the connection 1 form is going to be degenerate because all of the fibers are Reeb orbits and they're not isolated. And then I have that d lambda is just the pullback under the fibration map of omega. And I also know that if I push forward the contact distribution under the projection map or the bundle map, that I'm just going to get the tangent space of my base at every point. And the idea is then like, okay, great. Like I understand the Reeb dynamics, which is helpful if I want to try to construct or compute some homology theory, but all the Reeb orbits are degenerate. And so the idea is that you can use a Morse-Mail perturbation on the base to perturb the contact form. And then you can write down the perturbed Reeb vector field. And what's nice about this perturbed Reeb vector field is that if you're at a critical point of H, this term here is going to go away. And so you'll just be left with orbits which have to project to critical points of H, or the other types of orbits that you can get have to live over lifts of the Hamiltonian vector field on the base. But then that means they're going to be looping around some tori upstairs, and we have an epsilon parameter, and so we can make the actions of those extra orbits be arbitrarily large. And then we can set up a filtered chain complex by action so that below a given action threshold, the only chain complex generators are actually fibers over critical points. So this is like a bunch of math that associates all the things that I just said in math ways. So we've got our perturbed Reeb vector field, we have our action, and then just this dichotomy that if you pick an L that's appropriate to the choice of epsilon that you use to perturb your contact form, the Reeb orbit's going to be non-degenerate and project to fiber over a critical point, and if the action is bigger than that threshold, then either you're going to loop around a tori over an orbit of the Hamiltonian vector field on the base, or it's a larger iterate of a fiber over a critical point. We'll do like some direct limit systems so that we just have to care about the fibers over critical points. And we don't really have like time to do this, but the whole idea is just like, there's a nice trivialization that you can use. You can write down the Conley-Zander index of any Reeb orbit which projects to a critical point. And then you can classify the orbits as to whether or not they're elliptic or hyperbolic based on the Morse index of the point. So we're going to have an index 0 elliptic orbit, which we'll call E minus, an index 2 elliptic orbit, which we'll call E plus. Here, the index refers to the Morse index as opposed to the Conley-Zander index. And then you'll have 2G hyperbolic orbits if you assume that you use a perfect Morse function on the base. Okay, so then the theorem is that, well, we want morally embedded contact homology to be isomorphic to some kind of flavor of Morse theory of the base. And it turns out the flavor that it's isomorphic to is the exterior algebra of the homology of the base. Maybe that already doesn't sound like super friendly, but it's at least something. And you have this isomorphism as Z2 graded Z2 modules. You can actually like upgrade the isomorphism to be a relatively Z-graded isomorphism. And I have like a gross slide with all the formulas. It's the next thing coming up. But if you like sit down, well, maybe not you, but Morgan and I did sit down and think about this. And what's nice is that from this expression, if you think hard enough, you can just use the binomial coefficient theorem to conclude that for sufficiently large grading, if your genus is positive, that the ECH groups are just going to be isomorphic to Z mod 2 to the F of G, where F of G is this function 2 to the 2G minus 1. So you get a kind of like stability result for ECH. And if the genus of your base is 0, then you're going to be a 3-sphere or a lens space. And in that case, you can just write down the ECH and you get a Z2 in every even degree. So you already have a stability result. And kind of like the reason why you're getting this exterior algebra of the homology of the base is because the critical points of a perfect Morse function are giving you a basis for the homology of the base. But then once you get that basis for the homology of the base and you think about like what the generator sets are for embedded contact homology, you're going to end up with these tuples of Reeb orbits attached with some kind of multiplicity. And that's precisely giving you a basis for the exterior algebra of the homology of the base. And then in some sense, that's like a more straightforward kind of like combinatorial thing that you can just write down and like verify. And the much like harder thing to show is going to be that the ECH differential only counts cylinders, which corresponds to Morse flow lines on the base, because a priori, like it could include curves with higher genus, with multiple ends. And so it's kind of a surprise. Well, I don't know if it's a surprise. All these Floer theories always boil down to Morse theory. So maybe in that sense, it's not really such a surprise, but you end up being able to actually say that the ECH differential is just a sum of ways to apply the Morse differential to any of the HIs or E pluses. And so you're just going to count cylinders which project to Morse flow lines on the base.
Joe, did you try to do it over Z as well?
This is like the best you can do over Z. So you mean like Z coefficients?
Yeah.
No, we didn't want to think about orientations. And it wasn't clear that you get anything more by thinking about orientations. What we did do was like upgrade the grading. So if you have a first homology class, which corresponds to a non-torsion element, then you get a integral grading. Otherwise you get like a relative grading. And there's also like a substantial grading shift between ECH grading and the grading that naturally exists on the exterior algebra of the homology of the base. And then you can like write down the ECH index explicitly, because that's, I guess, what you're forced to do. And I just put in colors like what the different terms are. But Michael says this is a disgusting slide that nobody cares about. So, but then I told that to his students and they said that Michael was wrong because like nobody ever talks about the ECH index. So it's nice to see what's going on underneath the hood. But anyways, okay. Oh yeah, and then the other kind of like thing that I neglected to say previously was that when we were doing this like ECH counts correspond to cylinders, this is only true up to like some action threshold level. And so then you want to actually compute like all of ECH instead of ECH up to some action threshold. And so in order to do that, you need to use the fact that there's an isomorphism between Seiberg-Witten Floer homology and ECH, but action filtered. And that allows you to take direct limits so that you can send epsilon to 0 and L to infinity and actually recover all of the ECH. Okay, so in the last 10 or 5 minutes or whatever, I wanted to say something about like why might we want to use ECH to do something. So this is work that I've been doing with Morgan. And so the idea is that we want to say something about surface dynamics by way of Reeb dynamics. I probably won't quite get to the statement about surface dynamics, but I will try to like elucidate how you can use a knot filtration on embedded contact homology to get some kind of quantitative information about Reeb orbits and prove existence of Reeb orbit sets, which satisfy certain action and linking bounds. And so the way that you package 3 manifolds is often in terms of an open book decomposition. So it's a fact that every 3 manifold can be expressed as an open book decomposition. There's like a lot of words associated to open book decompositions. You're going to have some binding. In our case, we're going to be looking at T2Q torus knots, where Q is going to be odd. And then the open book is a fibration of the 3 manifold minus the binding to S1. And if you look at the pre-image of some angle inside of S1, that gives you a surface with boundary. The boundary of the surface is the binding, and the surface itself for every theta value needs to be diffeomorphic. And then the monodromy is going to be the self-diffeomorphism of the page. And open book decompositions generalize Milner's vibration theorem for hypersurface singularity. So that's kind of like their genesis. And so you can write everything down in coordinates. So T2Q can be realized as the set of points in S3. So that's Z1 squared plus Z2 to the Q is 0. And then you get a Milner vibration projection map just by taking the argument. And the page is going to be a surface of genus Q minus 1 over 2, where Q is odd. So that allows you to realize all surfaces of arbitrary genus. And then the open book that we construct in this way, the monodromy is going to be 2Q periodic. And so then that, in theory, should tell you something about 2Q periodic elements of the mapping class group of the surface. And then there's a cool visualization that an undergrad named Henry Blanchette made of Milner fibrations. So if you're ever like trying to explain open books and Milner fibrations to people, there are like some really cool interactive things. Okay, so then the question is like, great, we have this open book decomposition of S3 along a torus knot. How do we actually compute embedded contact homology? What are the orbit sets that we would want to use? And then how do we even compute the ECH index? And what Morgan and I were, we spent a lot of time thinking about this. And what we discovered was that you have to use, so in the pre-quantization bundle setting, everything is kind of too nice. Well, maybe I shouldn't say it's too nice. The pre-quantization bundle setting is very friendly, so it's relatively straightforward to write down the ECH index terms. And there's like a very nice trivialization coming from the bundle setup that you can use, and you can use that trivialization to compute every single term in the ECH index, and you don't really have to think too hard. In the case of this open book decomposition of S3 along a torus knot, we actually needed 3 different trivializations, and then we needed 3 different presentations of that manifold. So the first was in terms of the open book decomposition. The second was in terms of its ciphered fiber space structure. And the third was to realize the ciphered fiber space as an S1 Orbi bundle over weighted projective space. And then in this S1 Orbi bundle over weighted projective space, we could kind of play a similar game to what we did for the pre-quantization setting, where we looked at fibers which project to critical points of a Morse function on the base. Here, we needed to put like a Morse function on the base, which kind of like realizes the fact that we're looking at a 2Q periodic element of the mapping class group, which is realizing the pages. And you end up with an orbifold point of Z2 isotropy, an orbifold point of ZQ isotropy, and those correspond to orbits which are transverse to the pages. And then there's another orbit, which is the binding, and that projects to a regular point of weighted projective space. And by doing this like same game by perturbing by an appropriate Morse orbifold function, you get the generators of action filter embedded contact homology, which correspond to an elliptic and a hyperbolic orbit that are transverse to the pages, and the binding, which is another elliptic orbit. And then there's a knot filtration on ECH, which essentially realizes the action and linking of orbits. And this filtration is given with respect to the binding of the open book. It doesn't have to be a binding of the open book, but it's going to be really hard to compute the knot filtration if you don't have a presentation of your contact manifold as an open book. And there's this M times the rotation number of B, and this rotation number comes from the monodromy when you compute the Conley-Zander index with respect to a preferred trivialization. And then there's a linking number between the Reeb current alpha and the binding B. And in order to compute that linking number, it's helpful to know what the presentation is as an open book. And then Morgan and I computed knot filter ECH, and you basically end up with a Z2, provided that the knot filtration threshold is at least the kth element of these N2Q series. And if you've ever seen a talk about symplectic embeddings or ECH, you'll have seen these like NK2Qs show up. And so you're just writing down the kth element in a sequence of numbers where you do 2m plus qn, where m and n are non-negative integers. And so you just figure out what is the kth element, you allow things to repeat. And as long as the action threshold is at least that, then you'll have a non-zero ECH class in index 2K. And then otherwise in all other gradings, you'll get 0. And what's really remarkable about not filtered ECH in contrast to the ECH spectrum is that the ECH spectrum like heavily depends on the choice of contact form, and the ECH spectrum is essentially telling you the minimal action of homologically significant generators with respect to a fixed choice of contact form. But for not filtered ECH, it doesn't depend on the choice of contact form, provided that this binding orbit is preserved with respect to different choices of contact forms, and the rotation number of the binding is preserved. And then the way that we get quantitative bounds in existence for certain Reeb current sets is to use our computation of not filtered ECH and something called the ECH file law. So you can like put an epsilon. So I'll just end on this slide, and these are the like quantitative bounds that we get on orbit sets.
Are there any questions?
But what if you have a knot that's not a torus knot?
Then you have to figure out if there's an open book decomposition of S3 or whatever other manifold you're looking at.
But then can you compute these numbers as well?
So we can only we have a, let's see, we have an algorithm for computing the ECH index, but you still have to like do a lot of massaging of the numerology. So it's kind of like, you know, that you can compute embedded contact homology of any toric domain, but you still have to like sit down and like figure out how to like appropriately enumerate all the lattice point counts. Yeah. In this setting, it becomes like more subtle if you can't realize the open book as a ciphered fiber space. And even more subtle if you can't realize the ciphered fiber space is an S1 Orbi bundle, because then you're gonna need some more like sophisticated Morse spot methods in order to do the computations. And Morgan and I's work is the first non-toric computations of ECH, so there's pretty much like nothing known about what happens if you pick anything other than Huff link or an unknot. So this like T2Q example is the first, well, non-trivial knot in some sense.
I think I got a little bit lost. So can you know something about, well, you start with a torus knot
Yeah,
and your output is this not filtered ECH.
yeah.
Can it tell you something the way that the ECH spectrum, for example, tells you something about the dynamics of the
Yeah, so it's gonna tell you that if you're any contact form which admits a T2Q elliptic orbit with rotation number 2Q plus epsilon, then there has to be some Reeb current, which is not the binding. So you get existence of a Reeb current, which is not the binding, which is already kind of exciting, because you only knew there was one Reeb orbit, now you know that there's two. And then you get these bounds on the action. This top one is from the Weil law, and this second one is from the knot filtration. So it's telling you that the linking number of this new Reeb current, you know, has to exist with B plus like rotation number times M has to be greater than or equal to the kth element of like 2 plus epsilon over 2 and Q plus epsilon over Q.
And how do you get the existence of the second?
Oh, so you get the existence of the second because if this inequality is not true, then your not filtered ECH computation would not be valid because you have to have a homologically significant generator that has this action threshold, this action and linking threshold. And in some sense, like the computation of not filtered ECH, once you pass to a sufficiently large K, which corresponds to the ECH index, is basically telling you that you know that linking is somehow morally the action of the, describing the action of the Reeb orbits. But you can't, like, if you want to talk about the ECH spectrum for an arbitrary Reeb orbit, the most you can do is relate the square of the action to the volume of the manifold with respect to that choice of contact form.
Okay, so the knot filtration is basically very important here, right? Like,
Yeah. So the knot filtration has this topological invariance that the ECH capacities or the ECH spectrum don't have.
Okay, if there are any other questions, thank you.